Okay, guys. Yeah, coding lesson and beer review right now. So I'm drinking a Yingling traditional lager, and it's delicious. Okay. On my last video, I did a tutorial on how to write the Matlab simulation for um, for one gene being transcribed into RNA. And on that video, there was a comment, someone asking to see a tutorial for multiple genes. Um, so this is going to be that video. So I'm going to kind of breeze through this a little bit because a lot of this material I've already made other videos about in Python, but this will just be like converting it into MATLAB. So I'm going to kind of be breezing through a lot of stuff. So if you guys don't know what all these equations are and stuff, and if you're confused or anything, I'm going to be linking in the description to other videos I've done on this topic. So I recommend if anything in this video doesn't make sense, maybe check those out because those sort of go more in depth on like explaining all these equations and how to do like the basics of the Gillespie algorithm and stuff. But this is going to be kind of like breezing through, but taking what we've already done in Python and basically just doing it in MATLAB. Okay, so let's get started. So this is just an example system we're going to be using for the purposes of looking at a Gillespie simulation with more than one variable that we're keeping track of. So this is a 3-gene oscillating network that's based on the famous Goodwin oscillator. So it's 3 genes here: gene 1, gene 2, and gene 3. So gene 1 activates the transcription of gene 2, and then gene 2 activates the transcription of gene 3. And then gene 3 comes back around to repress the transcription of gene 1. And these terms here are called Hill functions. So again, if any of this doesn't make sense, I'm sort of like breezing over it. But if you guys want like a more in-depth explanation of all this stuff, I'll link to my previous videos that discussed all this stuff in depth. So yeah, these are the production terms here, and then we have for each gene also the degradation terms. And then to get the Gillespie algorithm set up, so these are the ODEs. We're not doing an ODE simulation, but this is like the ODE version of what we're going to be doing. So to convert from the ODEs to the Gillespie setup, we basically just need to think of all the things that can happen and then write down the appropriate rate for them. So, for example, if we have a production of gene 1, which means that gene 1, whatever level it's at, will be going to that level plus 1, the rate for that is going to be this term here, the production term. And then likewise, if we have gene 1, a degradation event happening, which means the level of gene 1 is going to gene 1 minus 1, the rate for that is this term here. And it's like that for all of the variables. So again, I sort of went through that pretty fast, but if you guys want like a more in-depth explanation, I'll link to the videos, the previous videos I did on this stuff. But okay, so let's get into the MATLAB code. So with MATLAB, I always start out with 3 lines at the top. So close all, clear all, and CLC. So right now there's nothing in the workspace, but if there was something, this will just like clear everything in the workspace and get us like a fresh blank state to start with. So I always just put those at the top. And then so the first thing we're going to do like to write the actual simulation is define some of our parameters for the simulation. So we're going to define some t end, which will be our end time. So I'll just make this 1,000 for now. And then so we need to define in the code all of these different terms. So gene 1, gene 2, and gene 3 are like the variables we're going to be keeping track of. But everything else here is just a constant. So C, N, all the K's and all the gammas, we need to just define these as constants in the code. So yeah, let's see. Okay. Sorry, I'm just gonna get these set up and then I'll explain. Okay, so I'll just keep for now. I'll just keep all of the production terms. I'll just make all of them 2, and then all of the all of the degradation terms, the gammas, I'll just make those 0.1 for now. But like I always say, I encourage you guys to like play around with different values of these and just kind of see what happens when you change them around and experiment around with them. I think that's a really good way to learn. And then so make n 9, and I'll make c 1. And again, if any of you guys are confused about like what these parameters mean, like the n's and the c's and stuff, if any of this is confusing, like I've been saying, I recommend checking out my previous videos where I go kind of more in depth on that. But I don't really want to like repeat material in that I've already done in previous videos. So if any of this is confusing, I'll just encourage you to like check out the previous videos on those. But for now, I'm just going to kind of go through it quickly. So next we want to do is make some arrays where we're going to be storing all of the values of our variables at each time point. So the first one will be the t array. So in Matlab, we can start out defining a dynamic array just by defining the first element in it without even like previously even having defined the array. So right now we haven't defined any t array at all, but Matlab lets us just like define the first value in it just right away. You know what I mean? Which I guess is kind of cool. But another thing to keep in mind is that with Matlab, the indexing starts at 1, not 0, which is kind of weird if you have any like experience with like other programming languages. Almost all of them, the indexing in arrays starts at 0, but for Matlab it actually starts at 1. So it's kind of the odd one out on that. But yeah. And then we're going to have a G1 array, and again just initialize that to start at 0. G2 array, also starting at 0. And a G3 array, yeah, also starting at 0. And again, I encourage you guys like play around with I mean, for the time one, I mean, I guess the time kind of has to start at 0, but I encourage you guys to like play around with different starting points for the genes and kind of see what happens with them. Okay, and then we're gonna have some counter variable I. Start at 1 to use for calling indices in the arrays. Okay, so the actual simulation is going to take place in a while loop. So we're going to see while t the last element of t, which is t index end, is less than our t end that we defined. We're going to say while this is true, we're going to execute our simulation. So the first thing we're going to do, like usual with the Gillespie simulations, is put all of our rates, all of these rates here. We're going to figure out what they are and then put them all in an array to kind of have them all together. So we're going to define, a rates array, initializing it with zeros. That will be, it'll have space for six numbers in there. And then we're going to say first element is going to be this here, because remember, if you guys have like watched the previous videos on the Gillespie algorithm, the rates themselves are dynamic, so they're changing because the rates actually depend on like what the current values of these things are. So the rates are actually changing as the values of the variables are changing. So this is why this is going to get like they're going to be like redefined every iteration of this while loop. Every time it executes, we need to like recompute whatever the rates are. Okay, so sorry for being lazy, but I'm actually gonna just copy and paste some of this stuff in, just because just being lazy. Sorry about that, but I'll still explain it. So I basically just copied and pasted all of this stuff right in here, and so you notice that to get the current value of gene 3, since we need whatever the current value of gene 3 is, to call the current value of gene 3 in our simulation, we just call the G3 array at index I, and we're going to be updating I, incrementing it each iteration of the while loop. So it'll always be giving us the most recent value of this array. Okay, so then we're going to do that for all of the different rates, and yes, this one's gamma 1 times the current value of gene 1. So again, to get the current value, we're just calling the gene 1 the gene 1 array at index I. So, and again, that rate's coming from here. Okay. So the third element of the rates array is going to be, going to be lazy again with the copy and pasting, but yeah. So basically, same idea. I'm just putting this rate here that we got from this term in the ODE, just putting this rate in here and making sure that we're calling the current value of gene 2 appropriately with using this I counter here to get the most recent value of gene 2. Yeah. Okay. Okay. And then yeah, so same thing for the degradation rate for gene 2. Just taking the rate from here, and just typing it in here. Oh yeah, so sorry, gonna be yeah, lazy one more time and just copy and paste this in here. Yeah, so just same idea as the other ones. Yeah. Okay. So now that we have all the rates in this rates array here, we're going to get the sum of it. We want the sum of all of the current values of the rates at this iteration of the while loop. So we're just going to call the sum function like that. Okay. And then, okay, so here's the first thing we're going to be choosing. So if you guys remember with the Gillespie algorithm, we first choose the time point of the next reaction, and then we choose which reaction that will be. Or and sorry, by reaction I just mean event. So we choose the time of the next event and then which event that will be. So the way we do this is that if we're at some time t, we're going to choose the next time point by picking some random number tau, and then just making the next time point the current time point plus tau. That's how we choose the next time point of the next event. And so the way we're going to choose tau is by taking a random draw from an exponential distribution, where the mean of that distribution is going to be 1 over the sum of the rates. So we're going to pick some. Oh yeah, so I better explain first. So one annoying thing about Matlab is that, as far as I know, like with Python, for example, you can just there's like a free the NumPy library you can use. It's a free library that you can use to take draws from like any distribution you could imagine, really. But with Matlab, as far as I know, if you want to like take draws from an exponential distribution, it wants you to buy like an extra package, like some statistical package software or something, to be able to use like their exponential distribution function. So I'm not going to do that, but luckily for us, there's a way to transform a uniformly distributed random number between 0 and 1. We can transform that into a draw from an exponential distribution. So the way we're going to do that is by taking random draw between 0 and 1 and calling that R1. So it'll be some random decimal between 0 and 1. And then tau is going to be 1 over the rate sum times the natural log of 1 over R1. So you guys might need to kind of take my word for this for now, but this is going to give us a random draw from an exponential distribution where the mean is 1 over the rate sum. Okay, so now that we have tau, we know that our next time point, which is going to be index I plus 1 of the t array, this is going to be the current time point, which is t index I plus tau. So that's how we pick the time point where the next event will be happening. Okay, so now that we've picked the time of the next event, we need to choose randomly which event that will be. So if you guys remember from like the previous Gillespie videos I've done, the way we're gonna pick which event the next event will be is basically just by taking a random choice where the probability of each event is weighted accordingly. So for example, the probability that the next event will be gene 1 getting incremented by 1 is going to be whatever the current value of this rate is, this whole term here, whatever the current value of all of this is, divided by the current sum of all of the rates. So that's how we weight the probability of choosing this event accordingly. And then so likewise, the probability that the next event will be gene 1 decreasing by 1. This will be this rate here, gamma 1 times G1, the current value of this rate, divided by the current sum of all of the rates. So that's just how we're weighting them accordingly, and of course it'll sum up to 1. And that's just, yeah, that's how we're setting the probabilities to weight them accordingly to make a random draw in a way that makes sense. Okay, so the code for this, even though it conceptually like is pretty simple and makes sense, the code is like kind of a lot. So yeah, sorry, I'm going to have to be lazy one more time and copy and paste. So sorry, yeah, apologize about this, but if I have to type it out again, it's just going to take too long. So you guys are going to have to, yeah, hopefully, like forgive me for this, but you have to just copy and paste all this, because yeah, it's kind of a lot. But even though it looks like a lot, I know it looks pretty intimidating. I'm going to go through and explain each part, and you're going to see how this code is just executing what we just talked about, just taking a random draw where each of these events is weighted properly. So that's all we're really trying to do with all of this code here, even though it looks pretty intimidating. So the first thing we're doing here is just taking another random draw of a random decimal between 0 and 1. So we're calling it R2 here. That's just what this is doing here, another random draw uniformly attributed between 0 and 1. And then, so the first thing to do is we want to check if this event is the one that's happening. So we want to check to see if we're randomly choosing this event with this random number. So the way we're checking is we're going to say, I'll explain on here first how we're doing it. So we're taking this random number between 0 and 1. We're going to take that random number and multiply it by the sum of all the rates, and then see where that product falls. So we're going to see, is it less than this rate? And if not, is it greater than this rate but less than, sorry, I should have said less than or equal to. Yeah, less than or equal to. So we're going to see, first, is that product less than or equal to this rate? And if not, is it greater than this rate but less than or equal to the sum of these two rates? And if not, then is it less? Is it greater than the sum of these two rates but less than or equal to the sum of all of these three rates? And then just keep going down the line like that. And whichever one it falls between, kind of, whichever one it ends up being less than that additional rate, we're going to choose that event. So if that product that we get by multiplying our random number by the sum of the rates is less than or equal to this first rate here, then we're going to choose this first event as the one that'll be happening. And then if not, if it's greater than this rate but less than or equal to the sum of these two rates, then we're going to choose this event here, gene 1 decreasing by 1. And then if it's not, though, if it's not these first two events, but we find that the product is greater than the sum of these two events, these two rates, but less than or equal to the sum of these three rates. If we find that to be the case, then we're going to choose this event here, gene 2 going up by 1. And so we're just going to go down like that and see where this random product falls between. And wherever we find it, we're going to just pick that event to be the one that happens. So this is just the code that's just basically saying all of that I just said. So I know it looks confusing, but really this is just checking to see if our random number times the sum of the rates is it less than or equal to the first number in the rates array. And if that's the case, we're going to choose this first event to be what happens. And then if that's not true, we say else if. Then the next condition is it greater than the current value of the first rate, but less than or equal to the current value of the sum of the first two rates. And then if that's true, then we know that the second event is going to be what happens, gene 1 going down by 1. And then we just go through each one. And check all these conditions to see where this random product kind of falls between. And so, by the way, it occurred to me that we don't even need like the first term in these if statements, because if this isn't true, if the random product isn't less than or equal to the current value of the first rate, then we already know that this part of the this condition here is true because it's redundant. So if this statement evaluates to false, we already know that that this part of this if statement will be true. So I'm kind of being a little bit inefficient by even writing out these first terms, checking if it's greater than some of the rates. This is kind of inefficient for me to write out, but I'm writing it out so that you guys can kind of see what's happening. But it is kind of redundant because we know that if this first if statement comes up false, then we know that the random product is greater than the first rate. So it's kind of redundant to write it, but I'm writing it anyway just so you guys can kind of hopefully follow what's going on. And then, so what do we do when we actually choose which event is happening? Well, when we choose which event is going to be the one that happens, what we have to do is update all of the variable arrays accordingly. And so that means we're gonna update whatever one's changing. And then, very importantly, because sometimes I forget this and get an error for forgetting this, but we have to also remember to update the other two arrays too, to just have their value at this time point be the same as the value of the last time point. So yeah, so let's say that we choose this first event to happen, and gene 1 is going up by 1. Then we're going to update the gene 1 array so that the next element in it, which is the index I plus 1, this will be equal to the current level of gene 1, which is index I plus 1. So basically just saying that here. And then we also have to remember to update the next element of gene 2 to be just the current level of gene 2, because gene 2 isn't changing. So we're just going to update it for the next element to be the same as the current element. And then same with gene 3. Gene 3 level isn't changing. So we're going to update the next item in gene 3 to be just the same as the current item. And then so for each one, it's just we change whichever one is changing, and then the other ones we add just whatever the current value it is. That'll also be the value at this new time point because it's not changing. Okay, and then so the next part, very, very important, something I forget a lot, and a common bug. Yeah, something that I forget, and I hope other people forget. I hope it's not just me, but we have to remember to increment our counter variable I. Okay, so let me just make sure I have everything. Looks okay. Hopefully it works. So yeah, so the next thing is let's try to plot the results. So we want to get 3 subplots here. So call it subplot, and then we say, yeah. So this is kind of the grid layout. This is how many rows we want, how many columns we want, and then which position we're going to be plotting in. I think. I'm not a Matlab expert. I think that's what it means. Don't quote me on that though, actually, but pretty sure that's what it means. And then so the first of these subplots we're going to plot our time points, and then our gene 1 values. Okay, and then let's also get a second subplot, and then plot the gene 2 values, and then yeah, third subplot, and plot the gene 3 values. Oh, and guys, remember, so just remember with the Gillespie algorithm, when you're getting the output, it's the time points, since they're randomly chosen, it's not going to be like evenly spaced. So that's just something to keep in mind. You can still like plot and visualize and stuff, but just keep in mind that the time points aren't going to be uniformly spaced. So just something kind of like a caveat to this whole simulation method. Just keep that in mind. But yeah, so let's see. Hopefully this works, but yeah, let's give it a try. Yeah, okay, so it appears to have worked okay and done what we were expecting. So as you can see, we're getting the oscillations because we have this cascade with a negative feedback loop. So again, if you guys want to hear more about how that's happening, check out my my earlier videos talking about this 3-gene oscillating model. But yeah, so it looks to have worked okay. So yeah, this first plot is gene 1, and then we have our gene 2, and then gene 3. And yeah, gene 3 looks to have like the clearest oscillating pattern, but you can also kind of see them in gene 1 and gene 2 also. Okay. Okay, so yeah. So thanks for watching, guys. And like I said, if any of this video seemed confusing or anything, sorry for kind of like going through it quickly, but I didn't want to like repeat material from previous videos. So if anything seemed confusing, I'll link in the description to more in-depth explanations on all this stuff really that I've previously covered about like the 3-gene model, what all of these like hill terms are and stuff, and then also the basics of the Gillespie algorithm. But also, if anyone has any questions, just let me know in the comments, and I'll try to answer them. Also, sorry, almost forgot. If anyone wants this code, I'll put the code like usual, just up on my GitHub, which I'll link to in the description if you guys want to download the code and run it for yourself. Also, guys, add me as a friend on GitHub if you want, because I only have 3 friends on GitHub right now. So if anyone wants to like send me a GitHub friend request, that would be awesome, because I only have 3 GitHub friends right now. So yeah. But yeah, this will be up on GitHub if you guys want to download it. I usually just, whenever I do like a MATLAB version of some Python code I already did, I try to keep the name the same, but just change instead of .py, it'll be .m. So my Python code for this topic was called Oscillator SSA.py. So I just called this one Oscillator SSA.m. But yeah, so it'll be up on GitHub if you guys want to download it. Yeah, so thanks for watching, and see you next time.